Hi, and welcome back to Codex. Our speaker today is James Murphy, who is an assistant professor of mathematics at Tufts University. Professor Murphy is known for his work at the intersection of harmonic analysis and data science. Today, he will speak about low-dimensional models for Wasserstein space. Take it away, James.
Hi, everyone. Thanks to the organizers for the kind invitation. So I'll talk about some mathematics and applied math and statistics, kind of at the intersection of probability theory, harmonic, what I would say is kind of a form of harmonic analysis and data science. So I just want to acknowledge some collaborators. So some of this work is led by graduate students, actually most of it. Ruji Zhang is in the electrical engineering department at Tufts, and Marshall Muller is in the math department. He's sort of like the lead on the second part of the talk on dictionary learning, and Matt Wierenski is in the computer science department at Tufts, but really is a mathematician who led on the first part of the work. And then I have some faculty collaborators, Shuchen Aaron and Abby Tassisa in engineering and math, respectively. So the context is statistical learning theory. So we're thinking about, in some sense, like the cursive dimensionality being an obstruction to certain learning problems. So this is, many ways to phrase this idea. The one that I think is maybe most classical is that if you take, uniform samples from in high dimensions, let's say a high dimensional cube, then points are far from each other. So it's going to be difficult to make inferences without lots and lots of samples to sort of drive these nearest neighbor distances close to zero. So pairwise distances, okay, on their own may not be informative. Okay, we all know this isn't really true. Like people do inferences on high dimensional objects all the time, right? Like genetic analysis is a thing, despite these observations being at a huge number of dimensions. So why does this work? How can you do statistics in these high-dimensional settings? I think that there's different practical explanations for this. One theoretical justification that I want to take as a kind of point of contrast from what we're going to do is what you might call it the manifold hypothesis or the manifold learning regime, which would say, okay, your data lives in high dimensions, but like secretly it's low dimensional. Like maybe it lives near like a low dimensional subspace, or to make it a little bit more rich and interesting, maybe it lives near like a low dimensional manifold, okay? And so what one would hope for is that if this manifold was low dimensional, then I could do all kinds of inference questions for my data where the number of samples I would need would depend crucially on the intrinsic dimension of this manifold. One could add some noise to this and say, okay, the noise is going to penalize me, but not too much. That's really what I care about is this intrinsic low dimensionality. So this sort of the idea that you would model data this way and sort of assume that high dimensional data sets have this kind of structure is the manifold hypothesis. So this was and is quite a popular, I think, mathematical model for high dimensional statistics, mostly popular, let's say, in the 2000s and 2010s. And I want to argue that despite its benefits, there are some regimes in which it's clearly not a reasonable model. So I'll just say that this idea of the manifold of sort of assuming your data has this low dimensional structure can lead to a lot of different nice algorithms that are can be quite efficient computationally and statistically. So this broad class of algorithms might fall under what are called like manifold learning schemes, where you're going to try to take little local information, little local nearest neighbor distances, let's say. These are going to be easy to make inference for because your manifold is locally flat. And then you have to stitch these things together to get like a global pattern, right? So the mantra might be something like think globally, fit locally, which is actually the name of a sort of very kind of well-known paper in this field. Lots of methods that maybe some of the audience are familiar with or have worked with fit kind of roughly into this regime. Things like computing geodesics on point clouds, things like isomap, Laplacian embeddings, Laplacian eigenmaps, diffusion maps, and related structural inference methods all kind of fit into this regime. I just want to give a very kind of simplistic toy example that illustrates why this might break down, but why even local pairwise computations aren't going to always be informative. So here's a really kind of simple toy data set, which is collections of images. All right, so they're going to all be black and white. And they're all going to be mostly black. There's going to be one white pixel in each image, but its location is moving, okay? So if I try to make any kind of inferences on a collection of images of this form, if I try to, let's say, vectorize these images, okay, so unroll them from 10 by 10 images into 100-dimensional vectors, These are going to be one sparse. But the problem for me is that if I do any kind of LP metric, any kind of Euclidean thing here, everything looks equally far from everything else, right? That, if the vectors are identical, the distance between them will be 0, and otherwise, let's say if I'm using Euclidean distances, it's going to be square root of 2, no matter where the support of this one pixel is. So in some sense, the manifold learning method regime has nothing to say here, right? Everything looks equally far from everything else. And the kind of thing you might observe here is that, well, what I really want to pay attention to in this toy example is the location of the support of the one point, right? So this maybe motivates thinking about comparing, objects, not so much in terms of Euclidean distances, but in terms of locations of supports of the relevant information. And this leads us to the idea of optimal transport. So one way to think of this is that it's sort of the correct geometry on the space of probability measures. And I'll try to give some illustrations for why geodesics in this space and notions of averaging in this space have sort of a pleasing visual representation from the standpoint of data science. But the origins of this sort of Wasserstein space is much older than kind of the image processing paradigm it's so nice for. So what's the setup here? So to make life easier, there's a lot of subtleties with this. To make life easy, we're going to consider the space of probability measures that have finite second moments and are absolutely continuous, so have associated density functions. And with these assumptions, lots of the definitions we're going to make are going to be well defined. So what we'll do is we'll consider a metric on this space of probability measures, the Wasserstein 2 metric. So what I'm going to do is define it variationally. I'm going to define it as the minimum over a space of maps T, which I'll say something about in a moment. And for each T, I'm going to look at the average displacement when I under the map T. So I'm going to look at averaging with respect to some probability measure mu, one of the measures I'm comparing. I'm going to look at, on average, how far the point X is moved by T of X. Okay, so the interesting part about this problem is this minimization. So I'm going to minimize over all maps T, which push forward mu onto nu, which is a condition that essentially says when I transfer probability mass from the input domain to the output domain under the map T, that sort of syncs up with the kind of assignments of probability masses that the measures mu and nu I'm comparing give. Okay, so let me give a little visualization that I got from Matthew Thorpe's very nice notes on this topic. What I'm showing in blue and orange is what this push forward condition really means, right? So I have a domain X and Y. For me, they're going to often be the same, but in principle, I could be mapping from across two different domains. And I have a sort of an assignment of mass given by these two probability measures, mu and nu. And what the push forward condition means is that when I take the sort of probability associated to a set with respect to mu, map it to the new domain, that's going to map onto sort of how the measure nu represents matters. So for me, the actual map that realizes this Wasserstein distance, right, the actual sort of displacement minimizing map is going to be really important. It's not always obvious that such a map exists, and in general, it may not. The sort of optimization problem here may have actually no feasible points, right? It may have there's nothing in this minimization. But under this assumption that my measures are absolutely continuous and have finite second moments, there is going to, in fact, be a unique map, which I'm going to call T star, which moves the probability mass from u onto nu in a sort of displacement minimizing way. So let me say a little bit about how to actually work with this problem. So the formulation I just gave is sort of an older version of this. This is sometimes called the Monge formulation because it roughly dates back to the 1780s and some work by Gaspard Monge, which turned out to not be very fruitful in the sense that doing the optimization over maps is a little bit hard to work with. And this problem sort of picked up again in the mid 20th century and is somehow associated with Leonid Kantorovich, who relaxed this problem down to something that starts to look more like a linear program. So what we'll do to define this Wasserstein distance alternatively is to take the minimum over all probability measures gamma on RD cross RD that have marginals corresponding to mu and to nu. And what we'll do is minimize the sort of average distance between points with respect to one of these joint probability measures, gamma. This is, as you can see, something that's starting to resemble like a linear program. The constraints on gamma are linear. They're just marginal constraints. And what is sort of remarkable about this relaxation is that it actually corresponds to the Monge problem under our assumptions. So what's the point here? The point is that when we're doing computations a little bit later, we'll be working with this kind of Kantorovich formulation, but in our case, it's really quite the same as the Monge problem. So from the mathematical standpoint, we're going to care a lot about the actual transport map T star. We're going to do a lot with this, but then computationally, we're going to work with this relaxed problem where one doesn't, obviously have a transport map T. One has this kind of diffuser coupling gamma. So the perspective that I want to sort of bring up here is, how can one think about sort of classical ideas like low dimensional sets, subspaces, submanifolds in the space of probability measures endowed with the Wasserstein metric. So let me just take a look at the chat. If anyone has any questions, just go ahead.
No, it's just the sign up for the mailing list.
People can and should just call out if anything's not clear. They have questions. So I guess the kind of overarching problem we were interested in was what's kind of like the right notion of subspace in this context, right? And what I mean is, a nice thing about modeling with subspaces is that statistical learning gets way easier, right? If I know that my data live on a subspace or close to a subspace, then the number of samples I might need to estimate things related to this is much lower. So we're thinking along the lines of, well, what corresponds to like a notion of intrinsically low dimensional set in Wasserstein space? How can I parameterize probability measures in a way that's going to make statistical learning efficient? So the kind of most natural question is, well, what's like the right notion of averaging in Wasserstein space? And one can kind of average probability distributions in a more naive way by just taking like mixtures, right? Where I would take some coefficients, take some measures, and say, okay, these coefficients correspond to like a multinomial distribution. I sample from that to figure out which measure I'm going to sample from, and then I take just samples from there. This winds up being kind of not the notion of averaging you get in Wasserstein space. And the right one, the one that we're going to work with, is the kind of barycentric version, or Wasserstein barycenters. And what this does is it says, okay, if you give me some probability measures mu1 through mu-p, and some weights associated to that, lambda, so these are going to live in the p-dimensional probability simplex, or I'm calling it delta p, but it's really p minus 1 dimensional, then I'm going to define the Wasserstein 2 barycenter as the measure nu, which minimizes the average squared Wasserstein distance from the reference measures mu I. So where does this idea come from? Let's imagine we're back in like a Euclidean space. I replace Wasserstein distance squared between the two objects with, let's say, Euclidean distance squared between two vectors. Then we know exactly how to solve this problem, right? We can differentiate and it's all very straightforward to get that this is the kind of classical weighted average in a linear space. Here, it's a little bit more subtle, but it's somehow the same basic idea that we want to find the measure which kind of on average sits closest to the reference measures in a Wasserstein sense. All kinds of questions of uniqueness and existence are not issues in this case because of this assumption of absolute continuity and finite second moments on the measures. So just as like a little kind of toy illustration, I'm going to imagine that these four measures on the top are the kind of atoms that I'm building from. So I want to understand how to combine these into a new measure. So if I just take a linear mixture, right, let's say with uniform coefficients, then what I'm going to do is say, okay, 1/4 of the time I'll sample from the first measure, 1/4 of the time from the second, 1/4 from the third, and 1/4 from the fourth. And if I think about that induced measure it looks like what's on the bottom left here, which has a couple of obvious properties. One is that its support is equal to the union of the supports of the kind of combined measures. Two, it does not, and for that reason, does not preserve any of the kind of structural properties of the underlying atoms, right? The underlying atoms were all Gaussian, their Euclidean mixture is a Gaussian mixture, which is not Gaussian. But I think the point I want to emphasize is that there is no capacity for new sample generation from the Euclidean mixture, right? That I can't do any kind of generative modeling with this, in the sense that any sample from the Euclidean mixture could have been got just by sampling from one of the atoms, right? There's no novelty coming out of this construction. The Wasserstein Barycenter is different in all these regards, right? For one thing, its support is not necessarily going to be the union of the supports of these things. It does preserve the structural properties in the sense that what I get is a Gaussian, and it itself has support that maybe wouldn't be so likely from any of the constituent atoms. So I want to argue that this is, essentially the right way to combine these things. The problem, of course, is that the linear mixtures are really easy to compute. Wasserstein Barycenters are challenging in this regard. Let me make one comment about the connection between Barycenter sort of geodesics and Wasserstein space. So if I think about taking a path between two one-dimensional probability measures, what I'm showing you here on the top is a blue Gaussian centered at about -2.5 and somewhat concentrated, and this is in one dimension, and a yellow Gaussian centered at about 12.5, a little bit more diffuse. What I'm showing you on the top are linear interpolations between these measures as t runs from 0 to 1. And what you're seeing is that just the relative sampling rates from these measures is decreasing, is sort of switching, right? So everything in between these things is not Gaussian. And what I'm showing you on the bottom is the Wasserstein geodesic, which in fact coincides with the Barycenter between these things. And the point I want to make is that the structure of these measures is preserved under sort of the Wasserstein geodesic and Barycenter constructions in a way that's not preserved in the linear setting. So this is sort of a I would say, trodden area of mathematics and statistics. And I'm going to try to somewhat phrase this like a harmonic analyst, which is to think about two kind of dual problems here. One is the question of how do I combine measures under this model, right? How do I synthesize reference measures into a Barycenter? Which is to say, how do I solve this synthesis problem that I've written here? How do I actually find nu, which makes this small? And this is sort of, I would just say, not necessarily the focus of what I'm interested in, right? This is going to be something that there's a lot of literature to draw on, going back to McCann's work in the kind of early 90s, and is sort of, I would say, a pretty active area of computation and statistics. As a little motivating example, I'm going to take some MNIST digits, this 3, 8, and 9, and put them on the vertices of this triangle here. And what I'm showing you in the middle are Barycenters that I computed from, or that were computed from the 3, 8, and 9 using different weights. Okay, so as I move along, like let's say this left edge of the triangle, I'm interpolating between 3 and 8 by putting increasing amounts of weight on, let's say, 3 or 8. And same along the other edges. In the middle, what I have is somehow like an average of 3, 8, and 9. And something I wanted to remark on is I didn't make this plot if I were to do this with linear interpolations. But what you would see there is I would basically just be doing the pixel-wise addition of these things and then dividing by 3, essentially. So you would see something that doesn't look like a digit at all if I did this in a linear sense. You would just be kind of putting all these images on top of each other. And there would be lots of kind of weird artifacts and things that would suggest that the linear construction is not the way to go.
Hey, James.
So
James. Yeah, so if I take a Barycenter between two measures, and I scale lambda 1 and lambda 2, like I imagine growing lambda 1 from 0 to 1 and shrinking lambda 2 from 1 to 0, would the curve that comes out be the same as the geodesic from one measure to the other in Wasserstein space?
It is.
Awesome.
Is, in fact. It's not, I mean, it's not super hard to show, but it does require, I mean, I think the kind of original proof of this requires going into the dual formulation of transport. So it's like a little bit like, I don't think you couldn't just do it in the back of an envelope, I don't think. Or I wouldn't know how It's a little bit technical,
Got
but
it.
it's something you want and it's true.
That's great.
Okay, other questions? Okay, so yeah, thinking from like a harmonic analyst, this is I'm going to call like the synthesis problem. So I have some generators. I want to combine them to get a new thing. How do I do that? Unfortunately for us, it requires solving an optimization problem, but it can be done. Lots of work on this. I'm interested in the so-called analysis problem, which would say, okay, I give you a set of generators, and then I think about all the stuff that can be written as barycentric combinations of those generators. So I'm going to call this Bary of mu1 through mu p. So these are all the barycenters which can be generated from these measures by changing the weights around. So you could think that like if we were in linear space and the coefficients were unconstrained, this would just be like a subspace, right? I have these sort of P generators, I take all their combinations. What do you get? Okay, it's linear subspace. Here we're constrained in that one, the weights are on this Pavilli simplex, and my method for reconstruction is your Wasserstein barycenter. So what we call the barycentric coding model identifies an element of this set with a coefficient lambda. And the intuition we have here is that, okay, P, the number of generators is small, then there is let's say a coefficient representation of this measure mu naught that is low dimensional, okay? So in some sense, learning this coefficient lambda, we would hope, let's say, depends statistically not on the dimension that these measures live in, but in, let's say, P, right? That the intrinsic dimension that's relevant here is not the dimension that these measures are supported in, but rather the number of generators in this model. So that was kind of our motivation here. So we call the problem of learning the optimal set of coefficients to represent mu naught the analysis problem. So this is, again, to someone who's sort of working in signal processing or computational harmonic analysis, I think that this is kind of this flavor of like getting coefficients in some basis of your choice, right? So someone comes into you with a set of things that they want to represent with. Maybe you hope it's like an orthonormal basis. Okay, they have very nice algorithms for getting the coefficients in this way, very efficient. Here, basic questions I think are not clear, right? I mean, well, that was at least the point of departure for us was, okay, if you have something in this barycentric span, can you give me an algorithm to actually find the optimal lambda? Right, we know that in fact there is some lambda for which this Wasserstein distance between my measure and the induced barycenter is 0. This is just like a tautology. What we were interested in is like, okay, is this lambda unique? Can we have some algorithms that actually tell us what to do? What happens if I just get samples from my measures? How can I estimate lambda efficiently? And this is something where there's a little bit of computational work in the literature. And I'll point to a paper by Boniel, Gabriel Perret, and Marco Chituri. But it's mostly, I mean, this paper is, and I think that what they have is a really kind of good algorithm that lets you try to estimate lambda this way. And we were interested in maybe more of the analysis of this. So the problem in the context of these like MNIST digits would be, okay, I give you 3, 8, and 9 on the vertices, and then I give you one of these mixed images. I want you to tell me the mixture weights, right? I want you to tell me that this, if I tell you what the pure 3, 8, and 9 are, and then I toss you the thing in the middle, tell me it's 1/3, 1/3, 1/3, right? Give me its sort of coefficient representation. Right. So in my mind, yes.
Do we expect the mixture weights to be unique?
Do we expect them to be unique? No. I mean, I'm going to draw for you like just a toy example where there is redundancy here. In some sense, like the question maybe is, are they generically unique? Like if I have like a distribution over measures, pick measures, and then look at the barycentric span, that I would expect is generic. Like this is like a probability 1 condition under that they'll be unique. But one can cook up examples where they're not. And I don't think it's like, I think it's in really not at all like a linear setting where, or finite, I shouldn't say it's not like a finite dimensional linear setting where like once you have so many generators, like uniqueness is impossible, right? Just by, sort of a dimensionality argument. I think it's not like that here, but one can cook up examples where there's non-uniqueness for sure. Okay, so actually let me just like get to that example. So are there unique coefficients here? Not necessarily, right? So I just drew for you a little simple example where I imagine P is 5, so these 5 generators. I could imagine a situation where a candidate measure mu naught lives on, let's say, the barycentric span of 3 of them, and also on the geodesic between mu1 and mu2 here. And so there would be 2 different ways with non-overlapping supports to represent this thing. I think that this is generically not going to happen, but obviously it can. So we'll say a little bit about this later. So the question that I think motivated most of this work was just, can you find for me a way to check if mu naught is in this barycentric span or not? Right? Can you give me an algorithm that, say, if I gave you perfect information about mu naught and the mu i's, or if I gave you samples from them, can you sort of do inference on this and check this question? And then the grander question would just be, can you project onto the barycentric span? In that, can you find for me a probability measure in the barycentric span closest to my measure of interest? And this is a harder question, I think. So what I'll do is I'll give you an answer to the second bullet point, both analytically and statistically, and then I'll give some partial work on the third question here. Then I'll show some applications. Right, so how can we exactly solve this question of projection, or rather, how can we exactly determine if you're in this barycentric span or not? So what we can show is that under some regularity conditions on the measures, so you should think something like, if they're compactly supported, then those compact supports kind of overlap in the right way, and that the densities associated to them are not like too degenerate, then I can check if mu naught is in this barycentric span by looking at the solution to a certain quadratic program. So I'm going to define the matrix A to be essentially the P by P gram matrix associated to my measures, in the sense that I'm going to compute the optimal transport map, Ti between mu naught and each mu I, look at the inner products of the associated displacement maps, right? So I'm going to take these optimal transport maps, subtract off the identity. You can think that this is like how much you're being displaced by each optimal transport map, and then take the inner product between those displacement maps and integrate with respect to mu naught. That's going to give me the entries of this matrix A. And so once I have A, I can look at the quadratic program, minimize lambda transpose A lambda, subject to lambda being in this probability simplex. So these are linear constraints, right? Lambdas have to be all non-negative and add up to 1. So I want to check if the solution to this program is 0 or not. If it's 0, then in fact mu naught is in the barycentric span, and if there's a unique minimum, then we're going to get the actual perfect barycentric coefficients this way. So the kind of couple of points I want to make here, which is on the plus side for us, the dimension of A is P by P, right? So if I have a small number of generators, A is a small matrix. So one might hope that, okay, you have like a simple problem in this regard. But what we're going to see is that we don't really have a way to beat the curse of dimensionality here, because estimating the entries of A is, at least the way we did it, is going to require us to estimate the optimal transport maps. And this is one of these, this is one of these hard problems that one would not expect to be able to beat the curse of dimensionality for generically. So that's a good thing, a bad thing. And then another good thing is at least we're going to have some efficient computational methods for getting the optimal transport maps, albeit they may be kind of not so good statistically. The other maybe downside of this is that this works in the case when mu naught is exactly in the barycentric span, so when there's exactly some coefficients, but it doesn't work in general, right? That solving this quadratic program in the case when mu naught isn't in the barycentric span, so you're going to get something other than 0 here, that in general, as far as we know, doesn't have anything to do with the optimal coefficients for projection, except in a few special cases where it does give you the optimal coefficients. And I'll say a little bit about that. So how does this work, like at a kind of a high level? The way it works is we think about what we call the variance functional, right? So this is going to be a map from the space of measures into R. And what it does is it says, okay, you give me basically a candidate measure nu, and I'm going to compute these sort of average distances to the mu i's, right? So the way to think about G lambda of nu is that if I fix lambda, the barycenter is the minimizer in nu. Okay, but here we're fixing nu and trying to understand what happens in lambda. Okay, so what we can do is essentially differentiate this with respect to lambda to get basically a condition on what it means to be a barycenter in terms of the lambda i's and the optimal transport maps ti's, right? So the key point is like from a sort of calculus standpoint, from the standpoint of like taking some derivatives to do optimization, is we want a condition on what about the optimal transport maps in lambda I will guarantee me that I have a Wasserstein barycenter. So we can basically argue that under our assumptions on regularity of the measures, we get the kind of right type of regularity on the transport maps, and therefore critical points of the variance functional will correspond to barycenters. And this essentially gives us the exact condition we want, because then I'll look at when do I have a critical point of this variance functional. It'll be when lambda transpose A lambda is equal to 0, essentially, just by breaking out this inner product on the left-hand side and writing it as this matrix problem. So, it's not too crazy, actually. And let me just say a little bit about, before I get into statistics, what can we do in general, right? So our general goal was to just find the best representation in the barycentric span. This requires me to do some projection, which in some sense, all this theorem that I just showed pertains to is projecting when the projected distance is 0, right? It's just giving me the coefficients. What happens if I'm not on the actual barycentric span? Can I still solve this quadratic program on the left, which I can always write out, right? This just requires me to compute the optimal transport maps between the reference measures and my target measure. Is that ever, in general, close to the true projected point? The answer is no, but in some special cases it is, right? So the special cases that give you this are what are sometimes called compatible measures, which is a term that I think is used in like different ways in this literature. What it means for me is that the optimal transport maps are really good collectively, in the sense that I have these n measures, and so I'm going to have, n choose 2 optimal transport maps between them. Okay, and these measures will be compatible if the optimal transport maps satisfy the following composition property: that the optimal transport map from the ith measure to the jth measure can be written as the composition of first going from I to k and then k to j for any choice of k and any I and j. So this is basically like a pretty strong condition that the way these measures interact is very simple. So what kinds of things satisfy this property? So as is often the case in optimal transport, things are easier and better in one dimension, and basically any absolutely continuous measures in one dimension satisfy this. Some more, like, let's say, non-trivial examples would be, Gaussian matrices with all having the same eigenvectors, with the covariance matrices having the same eigenvectors. And then if I have some base measure and all I do is radial transformations of it, then those will all be compatible. So it's a small subset of the space of possible measures, but if these things are, if you are compatible, then solving the quadratic program gives you the optimal projection coefficients. Something I guess we thought about is, can you move past this, right? Are there weaker conditions on the measures such that this quadratic program is useful? Can you get an upper bound on the projected distances from this quadratic program? This is all we know at this point. I'll go through this very quickly. I mean, I want to show some examples of what we can do with this from sort of a signal processing standpoint. How do people actually solve these optimal transport problems? If I give you samples, well, they would use the Kantorovich formulation. This is basically just a linear assignment problem. It can be done with cubic complexity, which is, the typical line on this is that that's not satisfactory. So there's been lots and lots of approximation schemes to this. I just have a very small number of papers I'm citing here. The approach that we took is kind of like the conventional wisdom in this community, as I understand it, which is to use the so-called entropically regularized form of the optimal transport problem, where instead of just solving this assignment problem, I penalize you if you don't have a diffuse coupling, right? So I'm going to add an entropy term to this optimization scheme with a balance parameter epsilon here. So I'm going to look for something that sort of assigns efficiently, but also is relatively diffuse in its sort of support, right? So this second term is going to prevent the coupling pi from concentrating too much. What's the reason to do this? This is strongly convex now, and we can use Sinkhorn's algorithm for matrix scaling to get like a pretty good and importantly parallelizable scheme for this. So it's basically computational. So the algorithm we actually use is to say, okay, if I give you samples from the measures mu0 and the reference measures mu1 through mu p, I'm going to compute an estimate on the optimal transport maps from mu0 to mu I. These are what I'm calling these entropic transport maps that were pioneered by John Niles Weed and his team at NYU. And the reason that we look at this entropic map is it's statistically efficient, right? That one can estimate the entropic map given samples really, really well. Okay, so we use these entropic estimators. We build the matrix A from the entropic estimates in the transport maps. And then we're basically just doing plug-in estimation, right? So I want to solve this quadratic program. I need to estimate the matrix A, which depends on the transport maps. I'm going to estimate the transport maps, plug those in to estimate A, and then solve for the problem with the sort of estimated matrix A in place of the true thing. So this is my algorithm. It's efficient in the sense that to get the entropic map is essentially quadratic in the number of samples, and I only have to do it p squared times, or p choose 2 times. So arguably this is fairly efficient computationally, and probably we can't do any better. Does it work, right? Does it give you a good estimate for the coefficients? And the answer is yes, but. Okay, so this theorem here just says the expected error between the true matrix element AI using the entropic map is, okay, it's going to 0 to infinity, so it's consistent. What rate? The bound on the right hand side, we have then that would be awesome. That would be a parametric rate. We don't get that, right? The second term is the dominant one. And okay, it depends on the smoothness of the optimal transport maps given by alpha. But the real thing to look at here is it's essentially n to the minus 1 over 4d. Okay, so this is strongly dependent on the dimensionality of the measures. Okay, so I get convergence, but I'm cursed by dimensionality. I have an exponential rate of convergence in the dimension. We have observed this in practice in some cases. Okay, so I think that this is essentially a limitation of our method, is that we can't estimate the coefficients in a dimension-independent way. But at least it's consistent, and it's sort of, in some sense, like the expected rate of convergence. We were hoping to do better, but we haven't been able to do it yet. We are working on some alternative ways of sort of thinking about the problem to actually be able to get parametric rates of convergence, which would mean essentially something like 1 over square root of n or 1 over n. But that's work in progress. Okay. I'll just show one quick example on how we use this, just as a very kind of toy signal processing task. If we think about doing things like image denoising or image in-painting, how might you think of this from a signal processing standpoint? Well, if you have like a collection of corrupted 4s, let's say, and you want to fix them, and you have a collection of good 4s, what you can do is try to find a set of good points that reconstruct your measure as good as possible, and then use that reconstruction as in place of the sort of crummy or corrupted data point that you have. So we can do that with linear estimation by sort of finding like a subspace of 4s that approximately generate my corrupted images. And what you get is what's in the second column here. And it's kind of, I think, what you would anticipate, which is that you have these kind of like artifacts that come from the fact that the linear reconstruction models are just going to add at each pixel value. So you're going to have like things stacking up on top of each other and giving you lots of, kind of nasty artifacts. If you use our approach, so the idea here would be you're going to pick some 4s and try to learn the optimal coefficients of the corrupted object with respect to the Wasserstein barycentric combinations to get the coefficients, then you get a, kind of a cleaner version of the problem, right? You get sort of a more crisp recovery, which I think, has some issues with regards to how it compares to the ground truth, right? The recoveries that we get in the third column are a little bit more diffuse and less concentrated than the true measures. But we think that's because we're using entropic optimal transport, in that, okay, if we had the computational wherewithal to solve the exact problem, that we think it would be a little bit sharper, but it is an artifact of our method. And I'll skip our examples with natural language processing, and let me just say for 5 minutes the problem of learning the reference measures, right? So the sort of dictionary learning problem here. So far we've assumed these reference measures mu1 through mu_p are fixed. Okay, well, I can ask, okay, they give you enough probability measures to use as training data. Can I actually learn optimal generators? I haven't given the sense of optimality, but I'll give a couple in a minute. Can we actually learn good ones, right? This is all over mathematical signal processing, of course, right? Maybe the easiest example is the idea of trying to learn like a good linear low-dimensional model for high-dimensional data via something like principal component analysis or singular value decomposition, depending on how you want to think of it. We would like to do that in Wasserstein space under this barycentric model. Okay, so this was, it was sort of in the air for a couple of years, but the paper I want to cite that produces like a really crisp version of this problem is the first author is Schmitz, and I think a lot of people on this paper, and it was in Cyan Imaging, maybe 2018, I think. And what they say is, okay, if I fix a dictionary D of probability measures and I let Bary D lambda be the barycenter associated with this set of probability measures and the coefficients lambda, I would like to find an optimal choice of D. I'm going to call that D star and corresponding lambda star, so that I can approximately reconstruct all of my observed measures mu1 through mu_n as barycentric combinations using the dictionary D. Okay, so the idea here would be is if m is much less than n, then you would not expect this to be equal to 0 generally, right? That you would be having some kind of compression coming out of learning a small number of measures that approximately represent all my training data. Of course, if m is greater than or equal to n, then this is a trivial problem. You just take the original training data as your dictionary and get 0 error. This is not actually a well-posed problem in general. It kind of for the same way, may not be well-posed in the linear case either, which is that if all of your training data live on, let's say, a Wasserstein geodesic, then there's going to be many probability measures mu tilde and let's say nu tilde that have the capacity to generate all the training data, right? So if in some sense your training data are like, I'm going to use air quotes collinear, right? But living on like a low-dimensional geodesic in Wasserstein space, there's going to be non-uniqueness of solution to this. So the approach that we were taking was we wanted to think about ways to make it well-posed. So what we did is we took the original reconstruction problem and added what we called a geometric regularizer, which essentially penalizes reconstructing using dictionary atoms that are far from me. Okay, so the regularizer is what I'm calling RG of dictionary lambda. And what it does is it penalizes if mu_i has a lot of coefficient weight on a dictionary atom dj, such that the Wasserstein distance between mu_i and dj is large. Okay, so this is saying, in the event of redundant representations, use the ones that are close to me. But kind of put that coefficient mass and concentrate it around my own atom. And this does solve the reconstruction problem. Also skip over the connection with K-means in Wasserstein space. So just to give a flavor for the kinds of results we have with this, we focus on like the hard version of this problem theoretically, where I try to minimize the kind of coefficient energy that goes on faraway points, subject to perfect reconstruction. So the soft version of this would be to have like a balance parameter that averages these things. But to write it like this, I can do a little bit of analysis and say that essentially this generically has a unique solution. And in fact, something kind of interesting happens, which is that if the dictionary atoms D1 through DJ kind of have the right configuration in Wasserstein space, you can actually get like sparsity and concentration to emerge in the coefficients. So in fact, not only does it solve the non-uniqueness problem, some kind of desirable structural properties come out of the coefficients if you solve it this way. Right. I mean, so how do we actually solve the dictionary learning problem? How do we actually like, get a machine that runs something? Our code is sort of publicly available, and I'm certainly happy to talk to you about it. Essentially, we do everything as is done in kind of the classical Wasserstein dictionary learning setting with sort of the new regularizer built in as needed. And I'll just say that, you know, compared to linear reconstructions or to the classical Wasserstein dictionary learning section with no regularization, the kinds of atoms that we learn, I think, are much clearer and more representative, at least in the case of learning MNIST generators from data. And, you know, we can run these in sort of some natural language processing tasks, which I skipped over earlier, and see a pretty good jump in performance when using our method. So we think it's worth doing. Just two open problems we're still thinking about. One is the what we call like the representational capacity or the approximation theory aspect of these Wasserstein Barycenter problems. You know, things are a little bit weird. I'll just say that, which is that, you know, let's say if you think like a statistical learning person, you know, kernel density estimators are pretty good for representing probability densities in L2, right? If you take mixtures of Gaussians, these are going to be dense in L2 because I can just keep adding more and more modes and keep making their, you know, variances smaller and smaller, so I can do estimation of any density. Gaussians are closed under barycentric combinations, right? So these kind of things you might do from the linear space to get like universal approximators with these barycentric spans, they don't hold up here. You know, and if you're interested in this, I can sort of give some pointers to like what we've been able to show and not show. But I think it's an interesting problem. And then a kind of a different framework that some other groups have been working on with this is the so-called linearized optimal transport framework, which gives a pretty big boost in computation and in some sense a totally different model for how to think about probability distributions and how they relate to each other, that I do think kind of could be built into somehow like a barycentric type model where one would reconstruct not by a Wasserstein Barycenters, but by a sort of maybe a more limited model that would be amenable to analysis. So I'll stop there, and these are the papers and the codes are on my website. And thanks for your attention.
All right, let's all smash that reaction button.
Yeah.
Are there any questions?